This is the Hacksmith Industries T60 Power Armor, a state-of-the-art exoskeleton designed from the ground up to offer unmatched performance in the field. Equipped with an augmented reality heads-up display featuring night vision, thermal vision, and zoom. Exoskeleton arms capable of curling over 300 pounds. Individually articulated fingers designed for crushing. And legs to balance and self-support the whole suit while being able to squat an entire car. Running the whole thing is a fully self-contained power pack featuring a 2 horsepower gas generator and a 2 kilowatt pneumatic air compressor. Armoring the entire thing is a 0.5 millimeter of super alloy called Nanovate, combined with 14 layers of Kevlar to provide unmatched bullet-stopping resistance. Featuring a state-of-the-art clamshell design for seamless user access, and to top it off, increased environmental resistance, including a fireproof outer layer and a full-body thermal regulation system for enhanced user comfort. This project has been the ultimate ambition, accumulating thousands of hours of work, tens of thousands of dollars, and years of expertise, and while other projects might have slowed us down, they did not hold us back. You've waited, and we've delivered. We're on the final cusp of completion, so join us for this journey on episode 9 of the Fallout Power Armor. Well, we've been prepping pieces to get nanovated, so we've actually been going through all the models and thinning out all the armor panels. You can see that right now a lot of these panels that we have on here are actually very thick. The problem is, in order to nanovate them, they have to have 100% infill. And if we make this whole thick piece at 100% infill, it's going to weigh a ton and it'll use up a ton of filament. So Andrew and Emmanuel have been going through all these pieces and making all the walls super thin. That's going to give us the room that we need inside to add all of our Kevlar, but also it's going to save us a ton of printing time and weight when these things get nanovated. So we don't want to rush that, because once the Nanovate goes on, there's no way to modify it. You can't drill through it, it's super hard to grind, you can't tap extra holes, you can't weld to it. So we want to make sure that the geometry is finalized before we send them off. Now you see, not all plastics nanovate equally. The process does require some elevated temperatures. So a lot of plastics like PLA or PETG can cause warping. Also, the cleaning procedure does use some solvents similar to acetone, which could dissolve things like ABS, which wouldn't be ideal. And while we have made some bulletproof armor samples out of ABS before, realistically we want a material that is both temperature and chemically resistant. Lucky for us, nylon fits that bill, and coincidentally it also proved to be the strongest during our bulletproof testing.
Give me a sec, I'm gonna go watch the original. Hold on, give me a sec. Are you recording right now?
I am.
So, we are printing a lot of our parts anew in carbon fiber nylon. So this filament is much more temperature resistant than PLA, PETG, etc. And crucially, it does not dissolve in those situations. Problem is, it's really annoying to print. These are the parts that I've printed so far, which are a little bit of a hodgepodge. We have some of them slightly processed, some of them not, and I have a full suit of armor to make. And that's not happening too quickly because of how difficult this is to print. I have a couple broken pieces over here. First of all, we've made our pieces very thin down. If you download the cosplay version that we provided on Fangs to get to make power armor on your own, you'll see that the parts are nice and thick, easy to print. These are not the same. They are super duper thin because of weight. If you're gonna print everything fully solid, which is another requirement for nanovating, you need fully solid parts, otherwise the metal will start precipitating on the inside and on the gaps between your layers, which is not something we want to deal with. It means that the plastic is a significant contributor to the weight of our part. So, they had to be really thin, which is also not good news for me, because really thin parts also break very easily. So I've been having some problems per se where, yeah, it's been difficult. But, we're trying some new things. If you take a gander at our fleet of bamboo printers, you'll see that some of the parts, we've been trying to print them on our H2Ss, right? These are single nozzle printers. They're going fine. Really big print capacity, great for the larger parts. But the problem is, with single nozzle printing, you need to have all the supports in the same material. First of all, printing supports in nylon is expensive, and ideally, we don't want to be throwing away that much money. And two, material adhesion of carbon fiber nylon is really strong. So we've been having problems where sometimes you can't tear off supports without actually damaging the underlying part. So what I'm looking into now is seeing, can we use any alternate materials? I've been working with ABS, first of all, as a support material in order to reduce those kind of errors. Hopefully, when we're going to be done, sand down all the parts to get them a nice smooth finish, coat them in metal, and then bada bing, bada boom, you got a suit of armor. Nope, not one.
Did that crack? Did that crack?
No,
Did you just break it? Did you just break it?
This is one of the more durable pieces, thankfully, so no.
You did break it.
Last one.
All right, so that makes up the first batch of all the parts that are gonna be sent off to Integran. We've gone through, thinned all the pieces, sanded them all down, added mounting studs to be able to actually tilt them, and these are ready for shipping. Let's go get them off to Integran. And make sure you check out Hacksmith.store, which allows us to keep making awesome projects just like this. We're here at Integran, and they've been working super hard to get all of our pieces nanovated, and these are looking amazing. These are coated in about 250 microns of Nanovate, making these things pretty much solid metal. They're gonna be incredibly tough, they're gonna be bullet resistant, and I cannot wait to get these back to our shop and installed on our suit. All right, so these parts are looking absolutely incredible, but I wanna see how they actually do the process to make something that's 3D printed into almost solid metal. Before any nanovating, the parts must go through an extensive 6-step cleaning as preparation, and only then can they go on to the main process. The Nanovate process can be broken down into 3 major steps. The first step is electroless nickel metallization, which is where the part gets its first conductive coating that will allow the copper in the next step to be electroplated onto it. So our power armor parts just went into the copper sulfate bath, so we're going to be electroplating them in a thin layer of copper, and this is going to improve the surface texture and the conductivity of these parts prior to them going into the Nanovate bath. Once our parts are electroplated in copper, they have to go through an additional 4 steps of cleaning to make sure that the copper is fully prepared for the Nanovate coating. And after all that prep work, our part is finally ready for the Nanovate bath to get its 200 micron coating over about 17 hours. And with our Nanovated parts in hand, we're ready to go back to the shop and install them on the power armor. All right, only another 45 parts to go. And while we're going all out and putting a 250 micron coating on all of our parts to give them insane strength, the same material can actually be used to manufacture incredibly small and precise components. Obviously at this point you know that Integran can coat pretty much anything in a super strong Nanovate alloy like our power armor. But you've also seen them make these really thin foil sheets, which we used as the backing plate in our bulletproof armor testing. But what I learned on my last visit is that they can actually use stereolithography to imprint any ultra high precision detail pattern onto the stainless sheet before growing the Nanovate. It's kind of like creating a film photograph. They use a negative of the pattern to actually create a thin layer of insulation that they expose onto the stainless steel sheet, which is where the Nanovate won't grow. So when they submerge the entire thing and they electroplate the stainless, this foil can now have extremely fine details for making things like MEMS devices, ultra fine micro sieves, microfluidics, or even stencils for high precision surface mount soldering. And they can do this with a bunch of different materials, including the same material we use for our power armor, which is their N1211, but they also have their N1210, which has high thermal stability, as well as other materials for electromagnetic shielding or thermal and electrical conductivity. That's pretty freaking sweet. We're gonna have to use this for a future project. But if you're interested to learn more, check out the link in the description.
There we go. Wonderful. Okay. These parts have been through a lot.
All right, so now that we've got all of the armor pieces thinned out in SolidWorks, printed in nylon carbon fiber, and sent off to Integran for nanovating, it's a perfect time for us to go through and improve all the tube routing on the legs and make the main manifold that is going to control the whole lower body. So I've got a manual here. He's going to be helping me out with that, and we're going to get started. If you remember in the last episode, the leg tubing was all kind of a mess. It was all hanging all over the place, half the cylinders weren't wired, and we had Caleb with manual controls controlling the legs for me. Obviously, that's not very intuitive, so the plan is we're going to get all the correct pneumatics routed up until the torso. We're going to make a nice bracket that's going to hold our entire manifold, and we're going to get everything plumbed in, get all the tubes out of the way to make sure that we don't get pinched when the legs are moving, and hopefully by then the parts from Integran are done and we'll be ready to armor the entire part. All right, so the first part of the pneumatics is actually our analog pressure regulator. If you remember this from the hands episode, we're going to actually mount this right into the abdomen right here because we have our air lines for the arms coming down to the section regardless. So that'll keep the tubing all nice and clean and allow us to then control the pressure going to our fingers so we have force control. So for the legs, we've got 4 important groups of cylinders. We've obviously got our main lifting cylinder over here, And the goal for these is to do the main 2,000 pound lift. But also, these are going to be very important for keeping the weight of the suit up. So what I'd like to do is actually partially pressurize these cylinders so that they have just enough force where they're keeping the weight of the suit up, but they're still maneuverable. The second one is actually these two lower cylinders down here. These are the cylinders that lower the calf section, which is going to go up against the ground and help stabilize the suit when it's standing upright with nobody in it. That way you can get in and out of the suit and have the suit be fully stable and not risk tipping over. So the third important group cylinder is actually our glutes, which are going to cover and hold your leg in place. And these are going to be paired up with the calf cylinders so that they open at the same time and release your legs. But we want that to open and close at a different time than the main chest. So we're actually going to wire the chest separately so that we can make sure that this calf section is on the ground and stabilizing the suit before we lift this heavy back plate all the way over your head and risk tipping the whole suit. And the final important pneumatic group is actually the ratchet locks. These are the ones that we installed on the legs to allow us to lock the legs and have the suit stand upright, unpowered with no air in the system without tipping over, or be able to lock the legs when you're lifting a heavy load to make sure that you don't need to keep using air to keep it in place. So this is the pneumatic manifold block we've come up with to actually control the lower body of the suit. Let me walk you through it. So you have 6 total valves as well as a pressure regulator. The first one here is going to control our ratchet locks, allowing us to lock the suit in position. The second one here is going to control the 2 pneumatics to the front that's actually going to raise the entire power pack. The third valve here is what's actually going to drop the calf and open the glutes. I'm going to skip over this one for now. We're going to go straight to here. These are the right and the left control valves for the main lifting cylinders. But what's interesting is that they're plumbed from both sides, one side through this pressure regulator. And we have this control valve here, which will actually switch between giving the system full pressure or giving the system regulated pressure. What that means is when we're trying to lift something very heavy, we can give the system full pressure and lift up to 2,000 pounds, or be able to pick up an entire car. But when we're trying to walk inside of the suit, we just want that pneumatic to support the weight of the suit itself without actually hindering our ability to bend the joint. By having the second valve, we can then switch the control air to go through the regulator, and we can set that to just have enough power to keep the weight of the suit up and assist in being able to walk. That's great and all, but we actually have to get this all mounted and plumbed, and for that, I'm going to pass it over to Emmanuel.
Yeah, let's do some pneumatics. Woo, don't put that in. So design and laser cut a quick bracket to mount the whole manifold assembly that's going right here into the, can I call this anything other than the crotch? The pelvic area?
The abdomen.
Is that, I thought, okay. So this is going right into the abdomen, so it's gonna go up here. All of these pneumatic harnesses are color coded because for both the A and B sections of all the cylinders. The blue tubes are going to be for locking.
Obviously, you gotta have your flow regulators in the lines so you can control how much air is going in and out.
Next up, solenoids. All right, next we're mounting the controller for the hands. All right, last thing, we need to hook up all of our lines.
All right, are we ready to power the system up?
Hell yeah.
All right, so I'm gonna give this thing air and let me know if anything moves too much. Oh. Giving the system air.
Something's happened. Oh, things are moving.
Things are leaking. Everything's leaking.
It sounds like it's taking off. Did it fucking, no! No!
All of these fittings, they're called push to connect because they're supposed to push the tube in.
My bad, Bogdan, I'm sorry.
Nope, there's a leak. Way too fast. Okay, leg shell. All right, so we've gone through all the tests. All the valves seem to be working properly, but there's a couple of cylinders that still need fine tuning on the flows and a couple of cylinders that need their directions flipped. So while the manual does that, I'm gonna start working on the actual code to open and close the suit to allow us to get in and out easily.
There's also some interesting readings that we're receiving via the controls. For example, a pressure sensor seems to just be not sensing pressure properly. So a lot of stuff to take a look at and maintenance.
Hey Manuel, check this out. Integran got our pieces all nanovated. Manuel? Manuel. Hey, Manuel. Sorry, dude, I completely forgot we switched co-ops. So this is our new co-op, David.
Hey guys.
Now that the suit has been all upgraded, we're ready to mount the nanovated pieces and the water cooling loop in the chest. Coming together pretty good. So basically the whole point of this cooling system is to give the suit environmental resistance. Because once you're inside the suit, it gets really, really hot. So this will help regulate the temperature of my body by heating or cooling the water within the power armor. And coincidentally, that's exactly what the sponsor of this video specializes in. While keeping the power armor cool is one thing, keeping your house cool and comfortable is probably a little more important. And that's where MRCOOL comes in. Their DIY heating and cooling systems use patented quick connect fittings, so you can install them all by yourself. No expensive specialty tools or professional contractors required. We actually have 8 MRCOOL units here at Herc, and we installed every one of them all by ourselves. They've become an essential part of keeping our shop comfortable year-round while we focus on the production of the Smith blade.
These are the 4 MRCOOL units that we installed ourselves for the tent. I've got 12 CNC machines in there running 24/7, so it's very important to keep them cool. I control all of that in the handy app, where I set a group for the tents and have all my units in there where I can control them with Wi-Fi.
Trust me, if I could fit a MRCOOL unit inside of the power armor, I would. But until then, if you want to keep your home comfortable, check out MRCOOL using our link in the description below. All right, let's get these parts on. All right, good? You have all the screws for it? Right onto the ground, nice and stable. That was awesome. It's really starting to come together. All right, let's power this thing on.
Don't hear any leaks.
Okay, so both bottom pieces are down, both these side pieces are open. Open, 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 nice, okay.
Oh,
Great start. So now if we go close, arms close, back closes, butt closes. Heck yeah. Now Owen, moment of truth, you ready? Woo-wee! You step into your suit, you hit this little latch button right there. Arms close, back closes, legs close.
I'm very surprised that nothing is breaking.
Let's try hand controls. Fist grip. Each finger individually. Finger gun. Pew! Hand controls are working properly. Okay, and then if I flip this switch from hand to leg control, I should be able to activate the leg cylinders. So you can see when I switch into there, it unlocks these ratchets. And then being able to press this, I should probably upload the most recent version of code before I try to test the most recent version of code. That would help. Okay, so that was completely my fault. I was working out of the wrong directory. I got the correct software on the suit now. Let me explain exactly what's happening. So basically, I've got the switch here, which sets the mode of the controls. Realistically, we only have a certain amount of buttons. I don't want to have an entire airplane cockpit of controls that I can't see in the hands. I want to be able to, through tactile, feel which button I need to press, right? So I'm only limited to 4 buttons and then the hand controls. Realistically, you're never going to be using the hands and trying to do something, pick something up or move something around while you're trying to walk. Usually you'll pick something up, log those hands in that position, and then try to walk. So what I have set up here is I've got the switch that changes between hand controls and leg controls. So when the switch is in leg mode, it'll actually unlock our ratchets over here. And then by pressing the thumb button, rather than controlling the hands, you can see right now it's still in hand control. But what should happen is that it should actually set control of the legs. So that gives us two different settings of low pressure and high pressure to either do lifting or to just support the weight of the suit. So the goal basically is you flip the switch, and based on that, you can either control the arms using the hand controls, the little force sensitive resistors we have on the hands, or the legs. So ideally you flip that one switch and then you can use the thumb buttons to actually actuate the legs. Because using the pressure from the pressure cuffs in the legs, the same way we did in the arms, is not really realistic, because when you're trying to push up on one leg, you have to push back on the other, and then that creates basically oscillations in the leg movements. We don't want that. So we're gonna make it nice and simple. Use the hand buttons to control the legs when we're in leg control mode, and then that was gonna allow us to walk in different pressure settings and make it super easy. Let's test it out. So the suit powers up in arm control mode. You can see we got full control of the hands. And then if we flip this switch here, now we're in leg control mode. So this right arm is now gonna control the right leg. Nice. So upon triggering the leg, it's actually gonna release the ratchets and then move the leg. And that's currently moving at full speed and full power. It's obviously been a flow regulator just to make sure that it's not, you know, snapping up and down too fast and breaking your legs. But then there's also a low pressure control mode. So if you watch on here, yeah? So now it's running that same leg without the ratchets. So we have a little bit more flexibility and we're not limited by which direction we can move in. And it's gonna be moving a little bit slower with a little bit less pressure. So this is just enough pressure to hold the weight of the suit up. As you can see, you can't even fully pick the leg up itself. Let's test the other side. 3, 2, 1, go.
Wow, that's perfectly insane.
All right, so the flow controls are all working properly. The main manifold is all working properly. The range of motion works properly. All right, and watch out. I'm just gonna open this. That's sweet. All right, so we've gotten all of our Peltier devices hooked up to the motor controller. We put another terminal block in here to make all the wiring easier. We've got 2 pumps, and then we've got the 2 loops that's gonna be going to the capron and into the G-force pans. So next step is just to fill it with water and see if it heats and cools that. Oh, we got a drip right here. It's, oh. Yeah, we gotta not get that on the solenoids. Yep, it's leaking in between here and here. I'm assuming we're gonna probably have more leaks than just that one.
This one actually looks pretty good.
Yeah, this one's way too loose. Okay. Leak looks gone. Let's keep filling it, I guess.
This one is not full, but I just filled it up to the point of where it would start leaking in the O-ring.
Okay, let's prime the pumps, I guess.
Oh, I think they're both running in the right direction. That's crazy.
Okay, that should be good then for these.
Wow, I'm actually so happy nothing is exploding.
I'm pretty damn happy with that. Nice job, David. Only 1 leak. Hot block, 54 Celsius.
Ooh.
The top at 14 right now. That's gonna be nice and cold for being up against my body. Honestly, this is a really exciting point in the suit because it seems pretty negligible, but when you're inside of the actual suit and you've got a layer of Kevlar, then an air bladder, then a layer of fireproof material, then the entire aluminum chassis, then 14 layers of bulletproof Kevlar, and all these Nanovate pieces with air trapped in between them, you get really, really hot, especially lugging around a 400-pound suit. So the cooling loop is meant to act exactly like an astronaut suit. It'll cool or heat the water and pump it through little tubes close to my body to keep me at the perfect temperature. All right, and with the thermal system working, it's time for us to mount the rest of the Nanovate pieces. We gotta put the chest piece on, the helmet, and the shoulders, and then we can test some of the suit's functionality.
Here, throw it on.
Let's throw it on.
Do we not need these first?
Just throw it on there.
Woo. Nice. Ow.
Why would you do
It works. So David went ahead and transferred all the electronics and the glasses and all the pneumatics to the new helmet. So we're ready to mount it on. Oh, look at that. That is sweet. All right, so with all those changes made, the purpose of this test is to do a full systems check. We have to make sure that all the pneumatics are still wired up correctly, that the legs properly move with a good range of motion, all the ratchets properly fire, and to double check that all of our hands and arms still function as they did before. The other thing we're going to be looking for is to make sure that the clamshell is properly open and closed and we can get in and out of the suit. We'll have to make full notes of all the system operation so that in the next episode when we do finishing touches, the suit will be ready for us to hopefully walk. So one of the last finishing touches we have to do is actually get all this sewn into one single piece and get this riveted into the inside of the legs and the inside of the chest. And then I'll be able to hop in and out of the suit without having to put all this on. And then the last thing we have to do is add the gas struts on the hips so that I can't tilt backwards and break my spine while I'm trying to waddle. But we are very, very close to having a full set of completed power armor. And I think next episode will be the last one. So the actual water cooling lines are gonna be running under the pants and under the apron to actually keep my body from, going to heat stroke. Yep, the one behind there as well. So this one, I believe this one connects to the right side. All right, ready? All right, moment of truth. David, you're gonna plug me in with the apron. Okay. Inflation complete. Does the headlight work? Headlight works. All right. Does somebody want to lift me up in the suit? Yep. Keep going. Fully off the ground. There we go. Leg tests in 3, 2, 1. All right, both legs at the same time. Curl test in 3, 2, 1. Nice, okay.
This is kind of crazy, yeah.
So finger tests. So I can lift this arm, but my left arm is jammed.
Do you want me to try to like move it out of the ratchet?
I think it's literally the flow control is probably wrong.
Spring locked. I knew this would happen. Oh!
How do you like my suit?
What if maybe these are like plumbed backwards, so it's trying to like keep them closed?
Yeah, it's totally backwards. Flip them. Be careful, there's air pressure, they will leak. Where my left shoulder is, there will be 2 tubes. One is marked green, one is marked yellow. They're 1/4-inch black tubes.
Yeah, but you want me to just let them?
Just let them leak, yeah.
Neither head pressure.
Okay, good.
Is that okay?
Yeah, that's fine. I'm trying to hold my arm in the middle, so.
All right.
All right.
They're swapped. Now we break his elbow.
There we go.
All right, shall we lower him from the armor stand and see him take his first steps?
I think we need those gas struts, honestly. I don't think I can actually hold the weight of the suit right now without those struts. I think let's call it. Woo! Man, we really need that water cooling. It is really hot in here.
You're sweating.
Yeah. Oh boy. Okay, well, overall, the suit is mostly functional. It's a couple of small quirks. One of the latches broke on this side. My right shoe was also loose. The 2 bolts that hold the shoe in, I think either popped through the shoe or loosened up. So I gotta make sure that those are secure. We obviously need to get the water cooling in because if I'm actually trying to walk and I'm waddling 400 pounds, even if it's self-supporting, I'm gonna get real hot in there, especially once we get all the Kevlar added in. But overall, the legs are moving, the arms are working, the thermal system is pumping water, and all the parts are nanovated. So we're making incredibly good progress. So I cannot wait to get this thing finished up in the next episode and put it through its limits. So stay tuned for that. That's a wrap.
Woo! Holy.